Okay, in this video we're going to talk about division models. And the first one we're going to talk about is the partition model. And sometimes people incorrectly call it the petition model. A petition is something that you have people sign if you want to get something done in terms of government. And a partition, P-A-R-T-I-T-I-O-N, means that we're going to be dividing things. Alright, so let's say I've got cookies here. And if we count the cookies, we can see that we have several. And 5 times 2 is 10. So we have 10 cookies. Alright, so let's divide. How could I divide those cookies equally between two people? So if I divided them equally between two people, then each person would get 5 cookies. Okay? I could also divide them equally between 5 people. So I could go through and depending on the level that you're teaching, you actually could do the division like I was trying to do with the pen, just cut it in groups. But I could simply say, okay, I'm going to divide this among 5 people. So I'll give 1, 2, 3, 4, 5, and then I go back and give more. Okay, 1, 2, 3, 4, 5. So that each person has 2 cookies. So I've divided 10 cookies equally among 5 people. Now, question, what about 9 cookies? Can I divide 9 cookies equally between 5 people? Or among 5 people? No, I can't, because I would still have this one here that only had 1 cookie while all the others had 2. Now, I could, though, take and divide 9 cookies equally between 3 people. So I would just go through and sort or count so that each person then has 3 cookies. Okay, so a partition model. Okay, now we can also look at the repeated subtraction model, and I typically don't go over it because it's just like the repeated addition model, just the reverse of it. Okay, now the missing factor model. Alright, let's take a look at 12 divided by 6. Okay, so in order to look at the missing factor model, I need to think about what is the related multiplication statement that would go with 12 divided by 6. And that would be 6 times some number equals 12. So this is the missing factor, because the factor is the answer that the factors are the 2 things that you multiply together to get the answer, which is the product. Okay? So the missing factor, 6 times what number is 12? So that would be 2. So that's the missing factor. 24 divided by 3 equals question mark. Alright, so that my missing factor would be 3 times something equals 24. So 3 times 8 equals 24. So the missing addend is the 8. Okay? Now, the division algorithm. Okay. I've got several things written here, and we'll just kind of look at this a minute. Now, we talked about the division algorithm when we were changing into bases. And the thing that we need to remember is that division is not closed under whole numbers. Now, an example of why that's true would be if I take 28 and try to divide it by 5, it has no meaning in the whole numbers because 5, there's not a missing factor, 5 times 5 or 5 times 6 that would get 28, okay? So this division fact has no meaning in the whole numbers, so division is, the whole numbers are not closed under division. Now, another way to look at this, we can identify this by the division algorithm by doing exactly what we did when we were changing bases. So I could say that 28 divided by 5, the dividend is the number that's under the division bar, the divisor is the number outside the division bar, and the quotient is the answer that you get, and any remainder that might be left, or anything that would be left when you subtract, would be then your remainder. So if I take 28 divided by 5 is equal to 5 times 5, which is 25, plus 3. So, in other words, 28 divided by 5 goes 5 times, and here's my example down here, divides 5 times 5 is 25, and then subtract and get 3. So 5 times 5 is plus 3. So your division algorithm says that 28 divides by 5 is equal to 5 remainder 3. Now, when we look at the division algorithm, we can identify that the number that you're talking about is equal to the quotient times some number plus the remainder, which is exactly what that's talking about. The quotient times some number plus the remainder. Okay, so the division algorithm. Okay? Now, let's look at multiplication and division as inverse operations. Okay, so 5 times 2 is 10. Then 10 divided by 2 is 5, or 10 divided by 5 is 2. All three of those facts are appropriate for thinking about partitioning or multiplying either one. If we looked at this as rows, 10 would equal 2 rows of 5, so you have a row here and a row here, or as columns, so 10 is equal to 5 columns of 2. Now, division without a remainder can always be shown as an area model. In other words, it makes a rectangle. Okay? Let me show you an example of that. Let me put some more paper over here. Alright, let's look at this area model that I've got. Okay, these are a different kind of cube, by the way. These are just called Lincoln cubes, and these are those very inexpensive cubes that I was talking about that pop on all 4 sides. Okay, one side has a nib, and then the other sides have the holes that they can be popped into, and they're kind of like Legos. Okay. So if I take this area model, okay, I can look at that, I can divide that in 2 pieces, okay? So let's look at my original piece. My original piece says that I have 1, 2, 3, 4, 5 rows, or let's look at it this way. It's probably easier to see since I've done the rows this way. Alright, I have 1, 2, 3, 4, 5, 6, 7 rows of 1, 2, 3, 4, 5 cubes. Okay. So let's see about partitioning this. Alright, so I'm going to pull it apart like this. Alright, so this could be 2 rows, okay, 2 rows of 5 plus 5 rows of 5. And this is actually the distributive property. This is saying that 7 times 5 is equal to 5 rows of 5 plus 5 or 2 rows of 5. Doesn't matter which way we show it, because think about this, then that's common, so I could pull that outside the parentheses, and then these 2 are left, and I have 5 plus 2. So this, in essence, is the same thing. 7 is the same thing as 5 plus 2, so it's exactly the same concept. Now, I could break this apart in other ways too. Okay? I could have said, here's another model. I could have said 3 rows of 5 and 4 rows of 5, or my whole piece was 1, 2, 3, 4, 5, 6, 7 rows of 5. So in other words, 7 rows of 5 is equal to 3 times 5 plus 4 times 5. Now, notice I've got the X there. At some point in time here, I interchangeably use the dot and the X. So know that when it's the small sign in between it, it does represent multiplication. So then in this case, I have a 5 in both. So I have 5 rows of 3 plus 4, which is another way to show 7 with 2 add-ins. So they break down into rectangles. Okay? Now, another thing that I like to do is think about factors of a number in general. And when children start looking at facts, for example, that whose product is 12. Alright, so let's think about that. What that means then is if their product is 12, something times something equals 12. So that means that I have 12 blocks. So let's see. There's 5, 10, 12. Alright, so how many different ways then could I put these together? Okay, let's see. Obviously I could do 4. Okay. So here's one array, okay? I can make a rectangle out of it, and it's 4 times 3 or 3 times 4, either one. Okay? Now there's one array. All right, I can make another array with 12 cubes. That would be 2 times 6, because I've got 12 cubes here. See, exactly the same number. Because if I pulled this apart and laid it like this, these 3 would look exactly like that. Okay? Now, so another set of factors then of the number 12 are 2 times 6 and 6 times 2. Okay, and my last set of factors, 3, 4, 5, 6, 7, 8. 10, 11, 12. All right, now, the last way that I've got, and I think I'm going to have to zoom out just a little bit. Okay, so we can see, and I've got 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, if I pulled this apart, I could pull this stick of 1 cubed by 12, and I could make all of these different arrays. So 1 times 12 equals 12, or 12 times 1 equals 12. Now remember, these are the same facts, all right? Because commutative property says I can switch the order. Okay, so it really doesn't matter. So if I were to write the factors then of 12, I would start out with 1. And here's how I like to show that. I like to show 1 on one end and 12 on the other, because this is the largest factors that you'll ever have. Okay, 1 and 12. All right, now, we had 2 then. 2 and 6. So we're working in 2, and the next one's 6. All right, now 3 and 4, and there's no number in between 3 and 4, so I know I've exhausted all my multiples. Not my multiples, I'm sorry, all my factors of 12. So all the numbers that multiply and get 12 would be 1 and 12, 2 and 6, 3 and 4. And that's all of my factor pairs. Now, this is a nice way to represent factors by doing 1 at the top, 1 at the bottom with the 1 and whatever it is, and then work in. Because when you get to the middle and you see that there's nothing that will factor, and you've got 2 numbers that are right next to each other, then you know that you've exhausted all of your products.